So it's my pleasure to welcome Tom Gannon from UCLA. He'll talk today about quantization of universal centralizer and central D modules.
Thank you all very much for having me. All of this is joined with Victor Ginzburg, and I was very excited for the opportunity to visit Georgia. I tried to visit for the sectional, but unfortunately, as you all probably know, it got canceled for the hurricane. So I'm happy to be here, at least in some form. Thank you all very much for having me. So today we're going to be talking about something in the Langlands program, and like a lot of things in the Langlands program, there can be a little bit of distance between what we're talking about and why we're talking about it. So first, I'm going to focus on the what we're talking about, because it more or less just uses basic ideas and representation theory of complex or reductive groups. But after a while, it's going to become like, okay, why are we talking about this? And then we will talk about the motivation behind the kind of work we're doing. But first, we're going to just start with the what. And the what just requires some elementary representation theory. So to start, let's let capital G be a complex reductive group. So I'm going to denote by G a complex reductive group. And if you don't feel comfortable with the generalities of complex reductive groups, you will lose no information today just by taking the examples of, for example, GLN, or maybe GLN modulo its center, or the group of matrices of determinant 1. All of these three, if you take these three groups, you will lose basically no information for the talk. And one of the first things that people think about when they study the representation theory of a complex reductive group is that there's a canonical representation associated to these types of groups that's associated to the fact that G itself is a manifold in addition to being a group. In other words, it's a Lie group or an algebraic group. And because of this, it has a canonical representation, namely the tangent space of the identity, otherwise known as the Lie algebra, which I'm going to denote as mathfrak G. This is, again, the tangent space of the identity point of G. And again, because this is a vector space with a G action, this is a canonical representation associated to G. And so you might imagine that in studying representation theory of such groups, it might be of interest to extract as much information as possible from this representation, given that it just can be defined without requiring any additional choices. In particular, one of the things that you might be interested in studying this representation is, for every individual point of my Lie algebra mathfrak G, you might be interested in the stabilizer of that point under this representation. I'm going to codify this as a definition. And the way I'm going to phrase it will encode the fact that this procedure of taking a point in the Lie algebra of G and asking for the centralizer in the group G has geometry attached to it. So the definition is the group scheme of centralizers is this thing that I'm going to write as Z sub G, and this by definition is the set of all elements G in the Lie group and T in the Lie algebra, or the tangent space of the identity, G times G, such that if I apply this canonical representation, or in other words, called the adjoint action of G, if I apply this canonical representation to this tangent vector, this is stabilized by the adjoint action of this G. For example, if G is GLN, well, GLN C is an open subset of the affine space Cn times n. It's cut out, it's given by the non-vanishing of the determinant. So it's an open subset of Cn times n. So it won't surprise you to find out that the tangent space of the identity of this open subset of Cn times n, or in other words, the Lie algebra, is just isomorphic to Cn times n, or in other words, the vector space of n by n complex matrices. In this case, the adjoint representation that I'm talking about is simply just given by conjugation of matrices. And so, in particular, this group scheme of centralizers for ZGLN is the set of all matrices M, invertible matrices M, I should say, and matrices T inside of GLN times the Lie algebra of GLN, such that if I take the adjoint action, which I described as conjugation, that's the identity, or in other words, M and T commute as matrices. So this is the group scheme of centralizers, and it's defined sort of a way to indicate that it has some geometric aspects to it. So one slightly geometric aspect that this thing has is that this group scheme of centralizers is just that, a so-called group scheme. What do I mean by this? Well, I mean not that literally ZG has a group structure, but what I mean is that there's a multiplication as long as you know that two elements centralize the same elements in the Lie algebra. In other words, I'm going to write ZG is a group scheme in other words, we have a map that serves like multiplication of a group map, ZG times over GZG to ZG, where we view ZG as a scheme over G by projection onto the second factor. So again, this isn't just saying you can multiply any two random elements GT, but what it is saying is if you have two elements G and G, which centralize the same element T in mathfrak G, then you can multiply them together using the group operation. We also have an identity section, and this is the full definition of what it means to be a group scheme. We're going to use this map to try and get some geometric understanding of what's going on with this group scheme of centralizers. And by the way, I know that this is over Zoom, but I hope all of you feel comfortable just interrupting me at any point and asking me questions, because it's a bit hard for me to see your hands if you have hands up or anything like that. So again, just please feel free to interrupt. But with that being said, we're going to use this map P, this projection map onto the second factor, to understand this group scheme of centralizers as some kind of bundle. But I use the word bundle kind of loosely here, as we'll see. So what people really like to say is that they view this group scheme ZG as a scheme over this vector space mathfrak G. And one way to understand sort of the geometry of what's going on in the situation is just try and query what is every single fiber of this map P. We're going to do this in the special case of G equals PGL2. I'm sorry, G equals GL2, and then later we'll talk about G equals PGL2. So in this case, like I said before, this is just understanding the group scheme of centralizers for GL2 is the same thing as asking, what is the set of all pairs? I'm going to move the whiteboard. What is the set of all pairs of matrices that commute where the matrix M has to be invertible? So I'm going to write this here as a table. So I'm going to write, if I pick a matrix T, a not necessarily invertible matrix T, which I think of as being in the Lie algebra of G, the centralizer of T is independent of conjugacy class. Its isomorphism class of the centralizer is independent of conjugacy class. So if we want to understand what this group scheme of centralizers is doing, we can just ask what a given matrix is conjugate to. And then we can ask for the centralizer of that matrix inside of GL2. It will also become convenient later to quotient by the center and think about what the center of this matrix is in PGL2. Now, because we're working in the complex setting, there's three cases for the conjugacy classes of a matrix in GL2. The first is the most generic. The first is if you pick a random matrix with probability 1, you will get a matrix that is conjugate to one of the form alpha 0, 0, beta, where alpha is not equal to beta. if you do this, you'll see that the centralizer in GL2 of this element T is given by, well, you can check that diagonal matrices form an abelian group. So diagonal matrices centralize this matrix. And because alpha is not equal to beta, you can also check that there are no other elements in the centralizer. So the center of this centralizer of this element is isomorphic to a torus, a complex torus, or in other words, the group C star times C star. So this is sort of the most basic case, but there are other, of course, types of conjugacy classes of matrices. Another conjugacy class that comes up is those matrices which are conjugates to one of the form alpha 1, 0, alpha, such that alpha is just some complex number. And in this case, you can reasonably ask, okay, what is the centralizer of this matrix? And you could check yourself that, well, one thing that happens in the centralizer is that you always still have the center of the matrix itself. So in other words, we still have a copy of the center of GL2, or in other words, this C star, this diagonal matrices with the same entry. But if you actually try to compute the center, you would also see that there's a copy of the additive group C as well. And so these groups are different, but they have a lot of features in common. For example, they have the same dimension and they're abelian. I think this similarity, I should say, is even better highlighted in the case of PGL2, where I quotient by the center. And you can check in that case, we just drop this copy of C star that corresponds to the center of GL2. And we see that the centralizer of this matrix in PGL2 is either C star in the generic case, or C in the slightly less generic case. However, there's one more case that I'm leaving out, which is kind of like anomalous and is very different than these other two cases. Namely, if we take a fiber of this map P at a point of the form alpha 0, 0, alpha, for alpha a complex number. Now, if alpha is not zero itself, then this alpha is literally in the center of GL2. And so you can check that indeed in all cases, the centralizer of this matrix is the entire group GL2. And similarly, the centralizer of the matrix alpha 0, 0, alpha inside of PGL2 is just the same, all of the group itself. And so I just want to sort of, if this is like maybe one of the first times you've delved into this kind of representation of complex or reductive groups, I just want to sort of emphasize the pattern that I'm trying to convey, which is that almost all the time, in a very strong sense, the centralizer of a matrix will be an abelian group of the same dimension. So like, for example, we had either C star times C star or C star times C. However, on a very, very small closed subset, and by very, very small, I mean mathematically precisely a codimension 3 or larger subset, there will be anomalous behavior that happens where the dimension of this centralizer jumps, assuming you don't have something tautological like your reductive group was secretly a torus or something like that. And so I want to make a word that kind of codifies the fact that almost all the time, like in a precise sense, the centralizer of a matrix, or the centralizer and element of the Lie algebra more generally, will be an abelian group of the same dimension. And the word I'm going to use for this is regular. So definition, we say that an element T, a tangent vector T inside of this Lie algebra G is regular if the centralizer in G of this element T, or in other words, the inverse image under this projection map, is an abelian group Now I could write of the same dimension. That's equivalent. I also could write a more standard definition of the word regular, which is that the centralizer has minimal dimension. These actually all turn out to be equivalent. So for the purposes of this talk, I'm going to use the definition that an element T is regular if its centralizer in the reductive group is abelian. And now I want to make a related definition, which is that I want to sort of understand this group scheme over the parts that are nice, or in other words, the parts that are abelian. So definition, let me put a line here. So definition, the group scheme of regular centralizers is this thing that I'm going to sometimes write G-reg, ZG-reg. And by definition, this is just the preimage of the regular elements under this projection map, where, again, this G-reg here is the regular elements of G. So in studying this group scheme of regular centralizers, one thing that was an observation of note that I'm going to build upon later of the talk is that in a precise algebro-geometric sense, the centralizer of a regular element is independent of conjugacy class. This is codified by the following proposition, which I believe in this language is originally due to no. And this proposition is just some algebro-geometric way, again, of saying that the centralizer is independent of conjugacy class. And it's for a regular element. And this says that the group scheme of regular centralizers descends to this so-called geometric invariant theory quotient, G mod G, which is just the Zariski spectrum of the functions, the G invariant functions on this Lie algebra. But in maybe more down-to-earth terms, what this means is there's a group scheme out there JG, and this group scheme is defined over this geometric invariant theory quotient G mod G. And there's an isomorphism where if I know sort of this abstract form of the centralizer for a certain conjugacy class, and I pick a regular element, then I should be able to extract an element in the group scheme of regular centralizers. Right now, what I'm telling you might not necessarily sound so deep because it's really just, I think everyone who studies this would agree, this is just more or less an observation. The observation is, again, that the centralizer of a regular element is really just independent of conjugacy class. So you can think of this group scheme JG, for example, as a scheme that lives over G mod G, and the fiber most of the time is going to be a copy of a torus or C star to the n. But sometimes it'll be more interesting. Let me scroll back for a second, show you that. Most of the time, the fiber of this group scheme will be a torus, but sometimes we'll have interesting non-torus behavior. Essentially, if the element is not this diagonal type, or in other words, semi-simple. So now might be a good time to make some interlude as to motivation. So we're going to switch gears for a second and come back to this later, but I just want to make some motivation from a new program of Ben-Zvi, Venkatesh called relative Langlands duality. So I'm going to write motivation via relative Langlands duality as to one possible reason you might want to study this. So this motivation is given by relative Langlands duality, which at first pass says that says conjectures. So the paper is 450 pages and it has a lot of conjectures that's making what I'm going to try and compile in 1/2 of a board precise. But please give me some benefit of the doubt. I'm trying to give you some heuristic of what this program is saying. And so This program, roughly speaking, conjectures that all instances of Langlands duality, both in the geometric Langlands program and the arithmetic Langlands program, should be indexed by a duality of so-called Hamiltonian G spaces. Which at first pass, if you don't know or feel like you care about this word Hamiltonian G space, one thing you can think of at first approximation is that a Hamiltonian G space is, roughly speaking, a scheme Y equipped with an action of a group, which moreover has a so-called moment map or map to the Lie algebra of the group, which is compatible with the respective G actions. So you don't really need to know what a Hamiltonian G space is for the purpose of this talk. I'm just saying that at first approximation, this is a scheme Y with a G action that lives compatibly over the scheme, over the Lie algebra of the group. And at second approximation, a more literal approximation, it also includes a Poisson structure, which satisfies a certain compatibility condition. But I won't use this Poisson structure for this talk. So for the purposes of this talk, you can take Hamiltonian G space and space with a G action which lives compatibly over the Lie algebra as interchangeable. Now, one reason that people want to study this group scheme of regular centralizers is that we'd like to apply the following representation theoretic trick to the group scheme, to a Hamiltonian G space. So the trick is the following. If you have a representation of a random group H, it can be often convenient to view that representation not just as a representation of H itself, but to view it, moreover, as having a commuting action of the center of H. That's just kind of a standard representation theoretic trick. And if your center is big, you can oftentimes work, say, one central character at a time. I don't necessarily want to make that precise. And part of the reason for this is that in the case of reductive groups, this trick, as naively stated, doesn't work. For example, the center of GLN, no matter what n is always one-dimensional. It's always a one-dimensional group. So the center just isn't that big. And moreover, if you work with PGLN instead of GLN, well, that's still a reductive group. It still contains a ton of interesting information about Langlands duality. However, the group literally just has no center. So there's a problem, which I'm just going to summarize by saying problem. The center of G is often small. And so we can't apply this great representation theoretic trick of having a commuting action of the center. However, because we're working in the context of these so-called Hamiltonian G spaces, or in other words, G spaces that live over the Lie algebra in a compatible way, a potential first answer to this problem is not to say that Y has a commuting action of the center, but because Y is spread out over this Lie algebra of the reductive group, it does have a commuting action of the group scheme of centralizers. And that's something that you could try and use. Now, in practice, if you tried to actually compute with this and see what was going on, you would see that you would run into issues that come from the following fact. I am about to scroll back to the table to indicate what following fact I'm talking about. And the following fact is that if I scroll back here, I see that there's a failure of this morphism P, where recall that P was the morphism from the group scheme ZG to the Lie algebra given by projecting onto the second factor. There's a failure of this morphism to be a bundle in a strong sense. More precisely, in the language of algebraic geometry, this morphism fails to be smooth And moreover, in the language of algebra, this morphism fails to be flat. You can show this as a map of affine schemes, and the corresponding ring map is just simply not a flat map. And this failure of flatness causes a lot of problems. However, so a potential first solution is to use this commuting action of the group scheme of centralizers. However, issues arise because ZG to the Lie algebra G is not flat. And in particular, therefore, it's not smooth. Now, one thing you might think of if you were trying to solve this problem is you might simply work with the group scheme of regular centralizers. So in other words, you might think potential second solution is to argue that any Hamiltonian G space Y has a commuting action of the group scheme of regular centralizers. It isn't difficult to see from the proof of Knopf's proposition that this group scheme of regular centralizers is smooth. So in particular, now you've solved one problem, the problem of the failure of the morphism to be smooth. However, if you restrict to just the regular elements of G, this definitely has the problem of defining the original problem away, right? Our first problem was that this morphism, this group scheme of centralizers ZG, which fundamentally captures the center for every element of the Lie algebra, the centralizer you have. And we said that morphism isn't flat, which causes problems. So it's not really an honest solution to just say, well, why don't we just work with the elements that are regular? And so just restrict to the points where this morphism is smooth. It just doesn't solve the problem. It just defines the problem away, which in practice essentially never works. However, one of the fundamental insights of Knop in his proof of the fundamental lemma about 15 years ago was that there is sort of a way to have a best of both worlds here and sort of have your cake and eat it too by using a smooth abelian group scheme that actually does tell you information about things that live over irregular points. So this is the first theorem in the second section of Knopf's proof of the fundamental lemma. And the theorem is that there is a morphism of group schemes where now I'm not taking JG and base changing it to the regular elements anymore up from the GIT quotient. I'm base changing it to all elements. And there's a morphism, JG times over G mod G with G, to this group scheme of all centralizers, which extends the isomorphism on the regular locus. And so I just want to make a remark, because it's not difficult to check that this group scheme JG down to G mod G is smooth, that this group scheme here, this fiber product I pictured with its map to G, is smooth and abelian. Therefore, this kind of does square away the problem we had before, which was that we needed a smooth abelian group scheme that had sort of content to it, but actually told us something non-trivial over every single point of the Lie algebra of G. And so I just want to maybe say out loud one of the main theorems of this talk before we do an example. So a conjecture of Nadler is that this morphism, this no morphism, or sometimes people call it the Knop-Ngô morphism, because it can also be derived from a more general construction of Knop that I don't want to necessarily get into right now, but this Knop-Ngô map quantizes. Now, I'm going to state this thing again in a more this conjecture in a more precise way, but one of the main theorems of this talk is this conjecture is true. But for now, let me actually give you an example of what this morphism is, so you can kind of appreciate that maybe this is some abstract morphism that can be applied in many, many situations. So for example, let's take again the case where G is GL2. In this case, the first thing we need to do if we want to understand this group scheme JG more explicitly is we need to understand this geometric invariant theory quotient of the Lie algebra of GL2 mod the group GL2. Now it turns out, and you can take this as a definition if you'd like, that in this geometric invariant theory quotient, any matrix is determined by its eigenvalues. So what I want to write here is that I want to write C2 or A2, depending on whether you're geometrically oriented or not. I'm going to write C2 because I'm pretty, I don't know, algebra geometrically oriented. But writing C2 is a little bit not the optimal way to phrase this. And the reason is because if I say a matrix is determined by its two eigenvalues and I write C2, well, C2 has an implicit ordering. So what I want to do if I really want to argue that this, thing is not ordered, is that I should replace this C2 with the geometric invariant theory quotient of C2 mod the symmetric group on two letters. And since I work primarily algebra geometrically, I want to give an algebra geometric model for this. There's two. The one that will become most convenient for me is, well, how can I possibly encode unordered eigenvalues? Well, one way to encode unordered eigenvalues is to just simply encode the polynomial that they solve. So in other words, this quotient can be identified with the set of monic degree 2 complex polynomials.
Right. Still have a question.
Oh, what's up?
So basically this comes from the Chevalier restriction theorem, is that right?
Yeah, this is literally the Chevalier restriction map.
All right.
Hey, Tom, can I ask you a question too?
Yes.
Is this no map injective?
No. Basically, except for being affine and birational, what I think is really interesting about the algebraic geometry of this map is it's not an open embedding, it's not a closed embedding, it's not a resolution of singularities. There's just many things that this map is not. And I will hopefully convince you of that because I'm about to give you the explicit example of the group GL2. So except for maybe being a morphism of affine varieties and therefore affine, it's surprising how much this group scheme can tell you things about G, given that the map relating the two is not many algebra geometric properties that you might expect. In particular, not injective. Okay, so I've told you that if we can now identify the base of this group scheme JG or JGL2. So this JGL2 is a group scheme that should live over C2 mod S2. Maybe I'll call this map P bar. Now, just like we tried to understand the group scheme of centralizers by understanding this fiber by fiber, we can understand this group scheme JGL2, which is sometimes called the group scheme of universal centralizers, by analyzing this map fiber by fiber. So it's reasonable to ask, given a complex degree 2 polynomial, Q of t, what is the preimage of this point under the polynomial? Now, I haven't told you how to define this group scheme JGL2. All I've told you that it's got some kind of universal property, right? You should be able to describe the structure of the centralizer of a regular element without appealing to the literal thing that this regular element is. Now, the algebrogeometric construction of this JGL2 is given by something called faithfully flat descent in Knopf's construction. There are also related constructions of Kazhdan and Lustig, where one can construct this by restricting to the group scheme of centralizers to a Kazhdan slice. But just to highlight this universality, I want to tell you what this inverse image is in the way that I think Knop was thinking of this when he originally came up with this, originally wrote down his proof of the fundamental lemma, where he constructed the fiber as follows. So remember, this fiber P inverse of Q of t means what is the centralizer of any matrix which is regular and whose characteristic polynomial is Q of t. So this is sort of the key observation here. We need to come up with a description of the centralizer of a regular matrix without appealing to the matrix itself. And here's the insight. The insight is that if you have a matrix M, then M always centralizes itself. Moreover, any scalar multiple of M centralizes M. Moreover, the square of M centralizes M. Moreover, any scalar multiple of the square of M centralizes M. And also, M to the 0, or in other words, the identity matrix, centralizes M. So this abstract form of this group scheme of universal centralizers, I want to say, is given by polynomials in one variable of M. However, as you all know, this contains redundant information. The reason being is a matrix always satisfies its characteristic polynomial. So because of this, it's better to say, and more correct to say, that this fiber, or the centralizer of a matrix which has characteristic polynomial Q of t and is regular, is given by polynomials in one variable modulo the fact that a matrix always solves its characteristic polynomial. Now, there's one more small point I have to mention if I actually want to be totally technically precise. It is true that the polynomials in a matrix always centralizes a matrix, but since we're working with the group version and not the Lie algebra version, I have to make some way to guarantee that my polynomial in a matrix is actually still invertible. One way you can do this is by just asking for the group of units of this ring. And this now gives you a literal answer of the fiber of this group scheme of universal centralizers. The centralizer of a regular element with characteristic polynomial Q of t looks like polynomials in one variable, mod Q of t, and then take the multiplicatively invertible elements. From here, the no map is easy. So I've learned from previous experience that it's a good time to pause right now for questions. Okay, so what is this no map? Well, what we've promised here is that if I have an element of this so-called universal centralizer group scheme, and I have an element, I have a 2x2 matrix with the same characteristic polynomial, I need to give you a recipe to compute an element of the group scheme of centralizers. Now, if I do this, what should I do? Well, I just told you that a fiber of JG is just some polynomial, let's say R of t, inside of this, the group of multiplicative units of this ring. And if I have a matrix M, what is this morphism that I'm telling you about, this so-called Knop-Ngô morphism? Well, this Knop-Ngô morphism is literally given by evaluating the polynomial at the actual matrix. So this is this no morphism, or Knop-Ngô morphism, depending on who you ask. Now, the construction of this morphism is pretty abstract, and I've given you one motivation for why one might want to actually construct such an abstract morphism from the point of view of relative Langlands duality. However, another motivation for constructing a morphism like this is actually done by Ngô, where in his proof of the fundamental lemma, he explains that this abstract morphism, this map that I've been discussing, is what he calls the abstract mold, where the symmetries of more concrete objects in representation theory and the Langlands programs, such as affine Springer fibers and the Hitchin system, the symmetries that you can find from these things can be understood as coming from this abstractly defined morphism. And so a lot of geometric representation theory is encoded in the fact that this morphism here, this morphism we've been calling the Knop-Ngô morphism, has such interesting properties, but isn't an open embedding, a closed embedding, a birational map, a resolution of singularities, or anything like that. And so, like, this is a slightly abstract map, but I just want to say that a lot of concrete things can be extracted from this map. In particular, this is one of the many deep insights used in Ngô's proof of the fundamental lemma. And so, again, our main theorem is that this thing quantizes. And so the next thing I want to talk about is, well, what exactly do I mean by this word quantization? Now, it is certainly possible to not do this trick, but I'm going to tell you how to quantize a slightly different morphism first. So first, I just want you to notice that by definition, we've been talking about this Knop-Ngô morphism. It's a map from this base changed group scheme to the centralizer of a general, the group scheme of centralizers. But by definition, the group scheme of centralizers is a closed subscheme of the group G times mathfrak G, or in other words, G times its Lie algebra. Now, it's a general fact that the group scheme G times the Lie algebra can be identified with the cotangent bundle of the group G. Here, I'm sweeping a small point under the rug, which I've been sweeping under the rug this whole time. Namely, I'm identifying the Lie algebra of G with its dual via some invariant form. But because of this, we can understand this morphism, this Knop-Ngô morphism, as coming from a map of affine schemes whose associated ring map is in the other direction, given by functions on the cotangent bundle, going back to functions on this group scheme of universal centralizers tensored up with G invariant functions on G with the functions on G itself. Now, I can say more precisely what I mean by this word quantization. Each of these four terms I've written here, namely OJG, CGG, CG, and the group scheme, the functions on the cotangent bundle, each of these four terms can be realized as the associated graded of a certain filtered object. For example, the ring of the ring of functions on the cotangent bundle can be understood as the associated graded of the ring of differential operators on the group G. Similarly, the functions on the scheme mathfrak G, or the Lie algebra of G, is sim of G Yeah, exactly. And so the filtration here is the universal enveloping algebra, which has a PBW filtration. This has a subset of the center, which can be identified as the G invariant elements of the universal enveloping algebra of G. And finally, maybe for the sake of time, I will only say very quickly what goes here. This is this so-called bi-Whittaker differential operators, or in other words, W is the bi-Whittaker reduction of this of the differential operator on G, just as one can show without too much difficulty that proposition, the group scheme of universal centralizers, as I mentioned a little bit before, can be identified with the bi-Whittaker Hamiltonian reduction, whatever this word means, of the cotangent bundle of our group G. Now, I know I only have a few minutes left because we started a few minutes after the hour. So first, I just want to state one of the first main theorems of our talk, of this talk. So a theorem in our preprint that we put on the archive, I think 2 weeks ago now, is that this Nadler conjecture is true in the sense that there is a morphism and many of the properties that you expect to quantize also quantize. So in other words, because both of these things are, because both of the things we've been talking about are group schemes, these both have a coalgebra structure. And this coalgebra structure quantizes to a so-called UG co-ring structure, or in other words, a coalgebra object structure in the category of UG bimodules. So the first statement of our one of our main theorems is there's a morphism of UG co-rings of all things that quantize the terms in the ring of functions or map on ring of functions associated to this Knop-Ngô morphism. This is the quantization of this Knop-Ngô morphism. Now, maybe for the sake of time, I will just mention somewhat quickly that just as Knop-Ngô realized that this morphism was sort of an abstract mold that you could specialize in other cases to get more concrete phenomena. We too, in our paper, specialize the construction of this morphism and use the ideas in the construction of this morphism to prove other concrete facts in representation theory. So for a remark, so using this morphism, we prove conjectures of Ben-Zvi and Gunningham, which they would say is an isomorphism of functors, but you can also write as an isomorphism of certain Harish-Chandra bimodules, or in other words, UG bimodules, which satisfy a certain integrability condition. So that's one thing we prove. And also using this Knop-Ngô morphism, we can also prove the following variant of an older conjecture of Braverman and Kazhdan. So I hope I said the word variant there. If I didn't, I meant to say the word variant, and I want to try and sort of convince you what this variant is and why this might give some idea of completing this so-called Braverman-Kazhdan program. So I haven't defined this word yet, but I can do it if someone asks me. So there is a conjecture of Braverman and Kazhdan in 2003, where they tried to give an alternate approach to proving Langlands functoriality via an exotic construction of automorphic L functions by as a proof of concept of this program, they formulated two conjectures, and I'm going to present one called the exactness conjecture right now. So the conjecture is convolution with a given gamma D module. I'm sorry, a given gamma sheaf. And you don't need to know what this word gamma sheaf is. I just want to sort of convince you what this variant will look like. Is exact on the category of L-adic sheaves on G of FQ, where GFQ is a finite reductive group defined over a finite field. And with the beauty of Zoom, I can just write over this theorem and write, this may be not dark enough. So I can write a theorem due to us, which we also prove in our paper, is that convolution with a given gamma D module is exact on the category of D modules on our complex reductive group G. So in this way, our techniques give us some insight on proving this Braverman and Kazhdan program. And one of the things we hope to do in the future is sort of use a spreading out argument to prove this conjecture and give an alternate proof of the vanishing conjecture in the setting of L-adic sheaves. I want to thank you all for having me, and I enjoyed being here. Thank you all again. Oh, okay, go ahead. I heard you. I heard no clapping, but I saw that people were clapping. I heard no clapping, but I hear someone talking. So
Any questions for the speaker? That doesn't seem to be the case, so let's thank Tom again for a great talk.